possible, we draw the free body diagram, then we'll try to derive the equations of motion. Then from the equation of motion, then we'll try to find out the natural frequencies for 2-degree freedom systems. We say there will be two natural frequencies, omega-1 and omega-2. Then based on that, we'll be able to find out the response of the system. And also we'll be looking into the model shapes, which is nothing but the displacements of the masses involved in the multi-degree freedom system. So basically multi-degree, what you see here is a 2-degree freedom system. So you need two variables to completely describe this system. So the first variable is x1, which is a function of time t, and the second variable is x2. So this system will have two equations of motion, and also it gives two natural frequencies. So there are many examples of this 2-degree freedom system. So here you can see an automobile suspension system. So here the suspension system, you can see the free body diagram here. So there is a pitch and there is a bounce of the system. So the bounce is along the y-axis. Okay, the pitch is the angular displacement. So if you want to describe the suspension system, then we need to have two equations of motion. Then we will be having two natural frequencies for the system. So here this is a case of a double pendulum. So here the two variables can be the linear variable x1 and x2, or we can also write the equations of motion in terms of the angular variables θ1 and θ2. Okay, so in the last class we have seen the derivation of this system. So applying Newton's law of motion, when you're dealing with a 2-degree freedom system, there are two masses. Okay, there are three springs connected with K1, K2, K3 stiffness constants. Then there are three dampers, C1, C2, C3. And the displacement of the mass M1 is given as x1, and the displacement of mass 2 is x2. So this system is subjected to external forces F1 and F2. So for such a system, we can easily derive the equations of motion by drawing the free body diagram for both the masses as shown here. Then we can write Newton's law, and from Newton's law, then we can modify this and we can express the equations of motion in matrix form. So always you will have a mass matrix M1, 0, 0, and 2 multiplied by the acceleration matrix. X1 double dot, X2 double dot is acceleration matrix. So followed by you have the damping matrix. Okay, C1 plus C2 minus C2, then minus C2, then you have C2 plus C3. So followed by the velocity matrix X1 dot and X2 dot. Then plus followed by the stiffness coefficient matrix. Okay, so this one is stiffness coefficient matrix multiplied by the displacement matrix. So generally a damper, a forced damping system, so 2-degree freedom, so we can write the equations of motion in matrix format like this. Okay, so in simple format you can write like this. Okay, so you have mass matrix, damping matrix, and stiffness matrix. So we can derive the equations of motion by two ways. One is by applying the Newton's method. So the other one is by applying the Lagrange's equations. So Lagrange's equation method is nothing but application of energy method. Okay, so let us see now. In this case, this is a 2-degree freedom system. Okay, the two stiffness matrices, stiffness constants K1 and K2, and masses M1 and M2, and there is no external force acting on this system. Okay, so we can write the equations of motion. Then again, you can see that we can write the two equations of motion in matrix multiplication format like this. So a mass matrix multiplied by the acceleration matrix followed by the stiffness matrix, that is K1 plus K2 minus K2 then minus K2, and you have K2 because there are only two spring constants here. So there is no external force, so the resulting matrix will have a zero matrix. So we can simply write the 2-degree freedom equations of motion in matrix form like this. So a mass matrix multiplied by the acceleration matrix plus the stiffness coefficient matrix multiplied by the displacement matrix. Okay, I'm skipping through this because we have done this in the last session. So now we can solve this 2-degree freedom system by taking the displacements x1 and x2 in this form: a sine omega t plus phi plus b sine omega t plus phi. So you can see that we need to, okay, ultimately we can solve the uh, equations, then we can come out with the two natural frequencies. Okay, you get a second order quadratic equation in terms of K1, K2, M1, and M2. So once you solve this quadratic equation, then you will be getting the two harmonic frequencies or the natural frequencies of the system, omega 1 and omega 2. Okay, so the solution of this, how to derive this, is the standard procedure. So we take x1 and x2 in the format of harmonic function, and then we take the first derivative, second derivative, then we substitute the values in this equation, then we simplify, and once you simplify, you will get this equation. And to get a non-trivial solutions for A and B, then we need to make sure that the derivative of this should be equated to 0. So if you find the value of this derivative, then it results into a quadratic equation. So by solving that, you can get the two natural frequencies. Now, another example here is a compound pendulum system. So we can also derive compound pendulum. So by applying the sum of moments acting on the system to 0. So similar to Newton's second law, but you are applying to angular motion or rotation. So here you can see the equations of motions can be represented again in matrix multiplication format. So here you have mass matrix multiplied by the angular acceleration matrix, theta double dot. So plus stiffness matrix multiplied by the angular displacement matrix. So you can solve the equations by taking theta 1 in this format and theta 2 in this format, and again you can solve the resulting 2 by 2 determinant, and then you will be able to get the two natural frequencies for the system. So for a coupled pendulum system like this, so you can get the expressions for the two natural frequencies like this. The methodology is exactly the same. So whatever we do for the spring system or the coupled pendulum system, so the way we get the equations of motion, then the analysis to get the two frequencies exactly will be the same. So now we looked into an example like this here. So in this case, so two masses are connected with two springs, okay, whose stiffness is K and K. So first, to find out the mode shapes, the natural frequencies, and the nodes for the system, okay, so we first write the equations of motion for the system. So the first mass is M. So the second mass is 3m. So we write the matrix for mass as M0, 0, 3m. So followed by acceleration matrix. So here the 2k comes K1 plus K2. So both stiffnesses are K, so we can write 2k. So here minus K2 is minus K. So minus K2 is minus K. So here K2 plus K3, K3 is not there, so only K. So followed by displacement matrix. So here, this is how you can straight away write the equations of motion in matrix format. So that is the main advantage. Now to get the two frequencies natural solution for this, okay, so you need to find out the determinant. So the equation is this. So you need to make sure that minus omega square m plus k should be equated to 0. Okay, so once you do that, then you get a quadratic equation, then you solve the quadratic equation, then you will end up with those two natural frequencies, omega 1 and omega 2. So the procedure is quite systematic. Okay, the next one, the energy method as applied to multi-degree freedom systems, then we'll write in the form of Lagrange's equations. So Lagrange's equations involves partial derivative. So when you're dealing with a generalized system with a damper, okay, then you can apply this. When there is no damper and the system is a conservative system, then you can apply this expression. Okay, so this is the energy method. So basically, you are doing the sum of the total energy, potential, kinetic, and dissipation energy. So we are equating with 0. But since it involves a variable, so you have the variables here Qi, then Qi dot. So if you are dealing with Xi, then you need to take here Xi dot. Okay, so then if you are taking theta I, then theta I dot. So depending on the number of degrees of freedom. Okay, so these are the basic equations for us to apply for multi-degree freedom systems to derive the equations of motion by applying the energy method. So in the last session, we have seen how we can calculate the partial derivatives, right? So we have looked into this equation. So here this equation has more than one variable. So therefore you cannot define total derivatives for this or the full derivatives for this. So this function can be differentiated one at a time. So when you're differentiating with one variable, we keep the other variables as constants. So you can see this example. We have done more calculations related to that. Okay, so this example is basically application of Lagrange's method. So there are only mass and the stiffness constant. So we basically write the free body diagram for the masses. Okay, then we write the kinetic energy, total kinetic energy in the system, and the total potential energy in the system. So the Lagrange L is equal to the potential energy minus kinetic energy. So you can write, so as you see here, L is kinetic energy minus potential energy. Okay, so total KE minus total PE. So therefore, we get the Lagrangian here. Okay, then we take the partial derivative of this. Okay, so first we do the partial derivative of Lagrangian with the velocity x1 dot. Then whatever you get, that one you are taking the full derivative with x. Okay, then minus the partial derivative of the L with x1. So once you equate this to 0, then you will get the first equation of motion like this. So this will be your first equation of motion. Okay, so the second equation of motion, then you are taking the partial derivative of L with x2 dot. Okay, x2 dot. So the velocity of the mass 2. Then minus partial derivative of L with respect to x2. So whatever you are getting here, partial derivative of L with the x2 dot, then you are taking the full derivative for this d by dt. Okay, so you can see this partial derivative of L with x2 dot gives you 2m x2 dot. Then if you take the full derivative of this, then you get 2m x2 double dot. So because 2m is a constant, and if you take the full derivative of x2 dot with t, then you get x2 double dot. So you just apply this equation, then do the partial differentiation and the total differentiation. The resulting equation will give you the second equation of motion. Okay, so like this, you can also find the third equation also. In this case, there are three masses, so third equation of motion. So this is the same Lagrange's equation. Now here the variable is x3 dot, and here the variable is x3. Okay, so we have seen L. So you take the partial derivative of L with x3 dot. So that gives you m x3 dot. Then if you take the full derivative of this, then that will result into m x3 double dot. So negative, then if you take the partial derivative of this, so that will result into the whole thing. So you'll have three terms here. So once you complete this differentiation, then you consolidate, you get the third equation of motion. So this is how you can apply the Lagrangian method to find the equations of motion. And once you have the equations of motion, you can represent it in the form of matrix. Then after that, you can find the natural frequencies, or you can find the mode shapes, or you can find the response of the system. Okay, so that follows. So Lagrangian method is basically to derive the equations of motion. So Newton's method, Lagrange's method. Lagrangian equations is mainly the energy method. So in the exams, end of term exams, definitely there will be a question from Lagrangian equation. So where you are applying this. Okay, so generally mechanical vibration exams, without a question from Lagrangian equations or application is cannot be avoided. So definitely there will be a question asked related to Lagrangian application of Lagrange's equation. All right, so this example is again applying Lagrange's method, so solving the same coupled pendulum. Okay, and you can see that the two equations of motions are listed here. So this is the first equation of motion, then this will be your second equation of motion. So these two equations you can combine together and write in matrix format. So just like we have done for the Newton's law. Okay, so then you can rewrite in matrix format. All right. Next, so we have seen now this, we have defined for this example, we have derived the equations of motion using the Newton's method. But this example tells you how you can apply the Lagrange's method to get the equations of motion. So I will not go through this. We have done in the last session. Okay, so you can see you can get the three equations of motions, and you can exactly write that in matrix multiplication format as we have done earlier. Okay, so then getting natural frequencies and mode shapes for a 2-degree freedom system. Okay, so without a damper and a free vibration. So this is a free vibration, okay, damper free. So there is no external force and no damper. Okay, so this is the equation of motion in matrix format. We can write like this. Now to find the response of the system, just like what we have done for single degree freedom system. So we now take the response in matrix format, and we take it as x1, x2 into exponential power e I omega t. Okay, so then you can see that to solve this, then you need to get this matrix multiplication to 0. So minus omega square mx plus kx must be 0. So to get a non-trivial solution, then this determinant must be 0. So you can expand this determinant, and you can solve for the two frequencies. Okay, two frequencies we have already seen. Let us say we know first frequency is omega 1 and the second frequency is omega 2. Then the displacements 2 1 and 2 2 you can find using this particular formula. Okay, so once you solve that, and you can simplify the final result for the two displacements corresponding to the two frequencies can be written like this. So now for omega 1 frequency, so you can write the mode shape like this. So the first displacement we always take it as 1. Okay, so with respect to this displacement, the displacement of the second mass. Okay, so similarly for the frequency 2, the displacement is 1, then with respect to that, so the displacement for the second one. Okay, so these are known as the mode shapes. Okay, so basically they are the displacements, how the masses are displayed. The displacement of the masses takes place. All right, so this is an example which we have seen in the last session also. Okay, earlier we have done for this omega 1 and omega 2. So now here I think we are solving the natural frequencies and the mode shapes. So first, based on the combination of the masses and stiffness coefficients, we can write the equation of motion in matrix format. So then you need to make sure that omega square negative M matrix, mass matrix into the displacement matrix minus Kx should be 0. So K is the stiffness coefficient matrix. Then X, the displacement matrix. So you need to be quite familiar with this formula to solve the natural frequencies. Okay, so now we apply this, then you can get a non-trivial solution for x1 and x2 other than 0 solution. So this determinant must be equated to 0. Then you can find the value of this determinant by cross multiplication. Then you get a quadratic equation. Then solve the quadratic equation. Then you get the two roots for the system. So once you have omega 1 and omega 2, then the mode shapes for the two frequencies you can calculate from the formulas given. Okay, so you will be applying these formulas for I think one of your assignment question. All right, so then the response of the system. So what we have done so far, so we know how to write the equations of motion in matrix format, either by Newton's method or by Lagrange's method. Then we know how to solve the determinant of the system to get the two natural frequencies. And once we know the natural frequencies, then we know how to get the mode shapes for the two masses. After that, then we need to find the response of the system. So that means the two displacements for the two masses are x1 and x2. So how we can write the response x1 and x2 for the system? So in terms of the given parameters. So now we follow exactly like the single degree of freedom system, but because now we have 2 degree, so we write in matrix format. And we take the response of the system in this format. So the first one is a constant A1 multiplied by the mode shapes x11 and x211. This we'll be knowing already. Okay, so multiplied by sine omega 1 t plus phi 1. So omega 1 is the first natural frequency, then phi 1 is the phase for the first mass. So plus a2 other constant, then this we know already, the mode shape. Then omega 2 also we know. So then we take the harmonic function a2 x sine omega t plus phi format. So this form is the same for single degree freedom. but now we are writing in matrix format. Now to solve this four constants A1, A2, phi1 and phi2, okay, then we need to know the initial conditions. We need to know the initial conditions. So once you know the initial conditions, then you have the formulas for the A1, A2, phi1, phi2. So the formulas are written in terms of other constants like C1, C2, C3, C4. So you can find those C1, C2, C3, C4 constants from the formula here. Okay, so these formulas will not change. Okay, if you are dealing with a mass and spring system, so the formulas will be always the same. All right, so then so that means once you know A1, A2, phi1, phi2, then you can write the full response of the system. So the response of the system means, so you just replace I remove here the annotations, then you just substitute your values in this expression. So you're solving A1, you're solving phi1. So you're solving A2 and you're solving phi2. So replace those values in this equation and that will be the response of your system. Okay, the 2-degree system with a mass and stiffness constant, a free vibration. All right, so to calculate A1, omega 1, A2, omega 2, so you need to know the initial conditions. Once you know the initial conditions, then you can use these expressions and can get the response of the system. So there's an example here. We have gone through this. So the initial conditions are there. So then we just, this is from the previous examples where we know omega 1, omega 2, and where we know the mode shapes, we know this also. Okay, so in addition to these two, then we also know the initial conditions as given here. So then we use the equations in the earlier slide. So we calculate C1, C2, C3, C4. Then we calculate A1, A2, phi1, phi2. So these values we substitute in this expression, and if possible, we simplify. So the final response is given in simplified format like this. So whatever may be the system, so the analysis follows like this. All right, so any questions so far, guys? I'm just revising what we have done in the last session. Okay, so now we start from here. Okay, in this, what we are doing is the free vibration of damped multi-degree freedom system. So we are adding damper now. So in the previous case, we only have mass and the stiffness constant spring system. So now it is a free vibration, but a damped vibration, damped and free vibration. So free vibration because there is no external force acting, and it is damped, means you are including the damping matrix. So for a 2-degree damped freedom system, so we can write the equations of motion in matrix format like this. So you have a zero matrix because there is no external force. Okay, so the external force is 0. So the derivation of this equations, you can follow either Newton's method or you can follow the Lagrange's equation. So now to solve this, okay, we go with the response just like the single degree freedom system with the damper. So we take the response matrix X as, so capital X into e power lambda t. Okay, so we need to find out here the X is the amplitude, so it can include X1 and X2 in matrix format. So to solve this expression, then we substitute the first derivative, second derivative, and substitute in the equations. Then we have this expression. So to solve this, you need to write lambda squared mass matrix multiplied by the acceleration matrix. So this should be acceleration matrix. Then lambda, the damping matrix multiplied by the velocity matrix. So this one you need to equate to 0. Then for non-trivial solutions, so then the determinant of this must be 0. Okay, so solving this equation, so you can write uh, the two roots for this. So in this case, the roots will be complex conjugates, means they'll come with an imaginary number I. So once you substitute, the modal shapes also can be written in this format. Okay, so here the first frequency omega 1 can be lambda 1 I, and omega 2 can be lambda 2 I. Okay, the final expression, the response can be written in this format. So once you solve all the constants A1, A2, okay, lambda 1 I, lambda 2 I, okay, so here you need to find out the values from initial conditions. So A1, A2, A3, A4. So these values you need to find from initial conditions. All right, now let us look at an example here. Okay, so consider the viscously damped 2-degree freedom system as shown here. Determine the natural frequencies, the mode shapes, and free vibration response. So if the initial conditions are given, so that means when time is 0, the displacement of mass 1 is 0. So when time is 0, the velocity of mass 1 is 0. So similarly, when the time is 0, the displacement of the mass 2 is 0. Then when time is 0, the velocity of mass 2 is given as 2 meters per second. So this is also how the masses, so your M1 is 1 kg, so your M2 is 2 kg. Okay, so then your K1 is 4 Newton per meter, your K2 is 6 Newton per meter, your K3 is 6 Newton per meter. Okay, so your C1 is 1 Newton second per meter, your C2 is also 1, and your C3 is 2. Okay, so to get the natural frequencies, then mode shapes and free vibration response, the first thing is we need to write the equation of motion in matrix format. So for the system, the equation of motion, now I just copied the diagram here. Okay, so first we write the mass matrix. So the mass matrix is M1, M2. Okay, so mass matrix is M1, 0, 0, M2. Okay, so you can see now M1 is 1, so M1 is 1, M2 is 0. So therefore, we write the mass matrix as 1, 0, 0, 2. Okay, so then the stiffness, okay, damping matrix. So damping matrix is the first element will be C1 plus C2. So the second element is minus C2. Then you have minus C2, then C2 plus C3. Okay, so we can write now based on this, so we correspond with the values. So C1 is 1 and C2 is 1. So C1 plus C2 is 2. Okay, then minus C2. So minus C2 is minus 1. So you have minus 1. Then this element is C2 plus C3. So C2 is 1, C3 is 2. So 1 plus 2 is 3. So therefore, you will get the damping matrix like this. So this will be your damping matrix. So multiplied by the velocity matrix. So the last one is your stiffness matrix. So the stiffness matrix, you can write it as K is equal to the stiffness matrix K. So you know it is K1 plus K2 minus K2. So K1 plus K2 minus K2. Then you have minus K2. So then you have K2 plus K3. Okay, so K1 plus K2, you can see K1 is 4, K2 is 2. So 4 plus 2 is 6. Minus K2. So minus K2 is minus 2. So I think you need to do this correction in your learning materials. So I think learning materials, it is printed as -1. So change it to -2. Then followed by the displacement. So this will be your equations of motion, so in matrix format. So we assume now the solution in the standard format, okay? 1x, so the displacement of the first mass, we take it as 1. So x is the amplitude, so exponential power lambda t. Okay, now to solve this expression, then we need to do the delta square minus plus delta square mx plus, I'm sorry, lambda square mx plus lambda cx plus kx should be 0. So I just go back to impress upon you the expression here. Yeah, so this is the one I was referring. Okay, so you need to make sure that this expression we need to write. Okay, so the same thing is applied here. Okay, so we are writing the same thing, and to get a non-trivial solution, so now you need to get the determinant of this. So you can write this now, the determinant. So lambda square plus 2 lambda plus 6, the first element, lambda square plus 2 lambda plus 6. So the second element will be here, this is lambda square will be 0. So you will have here lambda into -1 minus lambda, then -2. So the second element is lambda minus lambda minus 2. So similarly, the third one is minus lambda, lambda into -1 minus lambda, then -2. So here. So here the last element is lambda square into 2, 2 lambda square plus 3 lambda, lambda into 3 plus 8. Okay, so you get this determinant. You need to equate this to 0. So then you find out the magnitude of this determinant. So cross multiply, then you will get an equation of fourth order. Then you can solve that. You can reduce that into quadratic equation, and from quadratic equation you will be able to find the values for the complex conjugates lambda 1 and lambda 2. Okay. So here the two natural frequencies will be associated. Okay, you can write the damped natural frequencies omega 1 and omega 2 as by taking the imaginary part of the solution. Okay, so then you can equate that. Okay, this expression again, to get the two roots of the equation, we write this matrix format. So then x1, x2, the equations will be like this. So substitute all the values, then you will get the x1 value and x2 value in complex number notation. Okay, so this is how you can solve a question. I clear. Okay, when you have a question with mass, damper, and stiffness, a 2-degree freedom system without external force. So to completely solve the system, its natural frequencies, its mode shapes, and free vibration response. So the procedure is as shown in this example. Okay. So this is for a mass and damper and stiffness system. So you can write now the mode shapes corresponding to the first frequency and second frequency. So you have the formulas for this, so you can refer the formulas. So the complete response of the system, this is the guiding expression. So in this guiding expression, you write A1, A2, okay, you need to solve A3, A4, so you will get, okay, a 4 by 4 expression like this. Now this equation, you need to solve it. So solution of this equation is only possible by writing in matrix format. So you will have a coefficient matrix like this. So you end up getting 4 equations. So 4 equations, simultaneous equations. So you can write in matrix format. And if you solve this matrix, okay, so you will get the 4 values for the 4 constants and substitute this constant into the expression, then that gives you the complete response of the system, okay, the free vibration response of the system. All right, this type of questions will not be asked in the exams because basically we can't solve a 4 by 4 matrix without the help of a software. So you need to use a MATLAB or engineering equation solver or Minitab or any particular mathematical software need to be used. But this type of question is included in your assignment. So your last question is related to this example. So we'll try to touch upon that question. I'll provide you some of the basic guidance for that. So then you can work that question completely following this example. All right. So we now know how to get the response of a 2-degree freedom system, a damped free system. Okay. So now the last part of the multi-degree freedom system is that you are looking for a damped system subjected to harmonic force. So that means, okay, this is without damper. So you have a multi-degree freedom system damped but forced. Okay, so without damper but a force. So we consider the external force acting on the 2-degree freedom system again in matrix format. So the force matrix, you can write it as 2 by 2, so a column matrix, F1 and F2. Okay, so sine omega ft. Okay, there will be 2 frequencies for the omega also. Okay, so this is so this is the equation for a 2-degree freedom or a multi-degree freedom system subjected to an external force. So the force matrix is referred as, okay, a column matrix 2 by 2. Okay, a 2-element column matrix. Now the response of this, okay, the steady state response of this system you can write in this format. So just like the single degree freedom which we have done. So for single degree freedom system, we have just written x into sine omega t. So where capital X represents matrix, magnitude or amplitude. Now capital X is written as now the amplitude matrix. So you have 2 elements for this, x1 and x2. corresponding to the two masses M1 and M2. Okay, now the solution of this system to get the, okay, you need to write minus omega square mx plus kx is equal to f. So unlike the free vibration response where we have written minus omega square m, the mass matrix multiplied by the displacement matrix, okay, plus kx. Okay, so instead of 0 here, we have now the force matrix. So we write the force matrix here. Okay, so we can write the force matrix multiplied by sine omega ft. Okay, so we need to make sure that this is equated to the harmonic force matrix. So again, we can write in matrix format the same thing, minus omega square m, okay, plus k into x is equal to the force matrix. So if you solve this determinant, so you end up again getting two equations. Okay, so if you solve these two equations, that will give you the x1 and x2, the amplitudes of the two masses. So once you know the amplitudes, then you can write the response of the system as we have done earlier. Okay, now let us look at an example here. So this is the given system. Okay, so here I hope you guys can see this. So the M2 is subjected to a force 10 sine 2t. Okay, so M1 has no force, so there's no force acting on M1. So first we write the equations of motion for this system using the matrix format. So the first matrix is the mass matrix. So mass matrix is M1 0, 0, M2. So M1 is 1, so we write 1 here, 1, 0. Then this is 0, M2. M2 is 2. So we can write the mass matrix multiplied by the acceleration matrix plus the stiffness matrix. So stiffness matrix, the first element is K1 plus K2. So K1 is 1, K2 is 1. So 1 plus 1 is 2. Then minus K2. Minus K2 is minus 1. So this is K2. So minus K2 is minus 1. So you can write minus 1, minus 1. So this element is K2 plus K3. So K2 plus K3 is 2. So 1 plus 2. So you get the stiffness matrix as minus 2. I'm sorry, 2 minus 1 minus 1, 3. Okay, I clear this. So now is equal to the force matrix. So the first element of the force is 0. So there is no force on M1. So we can write 0. So the force element is now 10 sine omega t. Omega is 2 here. Okay. So this is 10 is the magnitude of the force. So you can write the magnitude of the force here, 10, then sine omega t. So omega in this case is 2. Okay. So this is how we can write the equation of motion for the system. So for a forced damped free vibration. So for the given system, the equations of motion. So then we can assume the solution for this in this format. So here x1, x2 are the amplitudes, sine omega t. Omega is of course 2 here. Okay. So now to get a non-trivial solution, so omega square minus omega square m, okay, m Okay, I just write matrix as capital mx plus kx should be 0. Okay, so minus omega square means omega is 2, right? So omega square is 2 with negative sign, minus omega square, minus 4. Okay, so this is minus omega square. So mass matrix multiplied by x, then stiffness matrix multiplied by x is equal to, so instead of 0, now we have the magnitude of the force. So 0 into, so we need to write this as the force matrix. All right. So now if you expand this, okay, and you will get the two equations like this. So you can expand this and write as two simultaneous equations. So the first equation is 0, the second equation will have 10. Okay. Now if you solve these two equations, then you will get x1 and x2 values. So these are the amplitudes of the displacements of mass 1 and mass 2. So you substitute x1, x2 values here. So that gives you the response of the system. All right, so the response of the system is shown here at the bottom. Okay, so the study response of the system we can write like this. So just substitute x1, x2 values in this equation here. All right, so you can just leave your answer here. So this one, you are just taking out the negative sign and introducing the phase as negative 90 degrees. Okay, so you can stop your answer here, or you can make both the magnitudes positive by including a phase here. All right, guys, any questions on this? I cleared the annotations. Okay, so this is a 2-degree freedom system with a damp-free but forced vibration. So there is an external force working. If there is a force and mass 1 also, then you, instead of 0, you have the magnitude of the force there. Okay, so the next part we'll be doing the damped state steady response under a force. So now we are taking the last part of the multi-degree freedom system. So we are including a forced and also a damped vibration. Okay, so you have not only the mass but also damper and stiffness, and the vibration is subjected to an external force. Okay, so here the force matrix for a 2-degree freedom system, so we can write the amplitude of the forces as F1 and F2. Okay, now the response for this system, just like the single degree freedom, so we need to write in terms of the sine and cosine functions. So with amplitudes U1, U2, and V1, V2. Okay, so this is for the steady state response. So because we are having a damper also here, so we choose the response of the system as given here. All right, so then the calculation is the same thing. So we can write, okay, so we need to find out the values U1, U2, V1, V2, then you'll be able to write the response of the system. Now let us look at an example given here. Okay, so here the force acting here is 2 sine 5t. So here the force acting is 3 sine 5t. So the force matrix so can be written as 2, 3 sine 5t. Okay, so 2 and 3 are the amplitudes, so both will have the same frequency, so you can write sine phi t. Okay, so the mass matrix, okay, m1 0 0 m2, so m1 is 2, so followed by 0, then 0 and m2, m2 is 1. So this is the mass matrix. So stiffness damper matrix, the first element will be C2 plus C3. So C2 is, sorry, C1 plus C2. So 10 plus 20, that is 30 here. Minus C2. So the C2 is negative 20. So minus C2 is minus 20. So here also minus C2 minus 20. Then plus C2 plus C3. So we don't have C2, C3. C3 is 0. So C2 plus C3 is just 20. So this is your damping matrix. Then the stiffness matrix. So the first element is K1 plus K2. So 200 plus 100. So this will be your K1. So here will be K2. So 100 plus 200, you get negative 300. Then minus K2. Oh, minus, okay. So the first one is K2 plus K1 plus K2, then minus K2, sorry. Minus K2 is minus 200. I think this should be minus 100 as we can see, not 200. So this should be minus 100. So the last element will be K2 plus K3. So K2 plus K3 will be 300 plus 100. So this will be your K3. Okay, so this will be now 300, 1 minus 100, then minus 100 and 400. So you can do this correction in the learning material. Okay, so we can assume the solution in this format. Okay, now to solve this, then we need to the same matrix. So you have to write the whole matrix here. Okay. So then elaborate this and write in terms of the determinant for coefficients for sine phi t and cos phi t. Then you can write as 4 by 4 determinant like this matrix. So if you solve this, then you will be able to get the 4 unknown variables. So u1, u2, v1, v2. Then substitute back in the response equation. So that will give you the steady state response for the damped and forced system. So you can see in this question and the previous question, wherever you get with a 4 by 4 determinant, okay, this type of questions will not be asked in the exams. So simply because you can't solve a 4 by 4 matrix without the help of calculators, programmable calculators. All right, so that ends all the topics from your learning guide for the mechanical vibration course. Okay, so normally the exam will have 5 or 6 questions, and there will be 2 questions will be asked from multi-degree freedom systems, and the remaining 4 questions will be from single degree freedom systems. All right, guys, any questions on multi-degree freedom systems? Any doubts, let me know. So the first important thing under this is solving getting the equations of motion for a multi-degree freedom systems using Lagrange's equation. So there's one question will be definitely asked related to that. Then another question that will be asked may be, solving the expression a multi-degree freedom system for a simple mass and spring system, with force or without force. All right. Any questions, let me know. I think we have done all the assignment questions, right? Yes, I know Azhar has reminded we have not done the last question. Okay, let me see what is the last question. Yeah. Uh, okay, so uh, this is the last question, right? So you are asked to determine the damp-free vibration response. So here you are asked to find damp-free vibration response. So there is no force acting, but the system has a damper. Okay. So for the system shown in the figure, if the lower mass is given an initial displacement, so this is the displacement of the lower mass. So that means the displacement for x2. The upper mass is held in its equilibrium position. Then the system is released. Okay, so the displacement of the upper mass is in equilibrium position. Okay, the values of mass given, the damper is given, the stiffness is given. So the equations of motion were derived. So that means there is no need to derive the equations of motion. So the equations of motion are given here. All right. So I think all of you have the question with you, right? I'll be using the camera to write few things. Okay, so uh, so the initial conditions are given for the system, right? So initial conditions we write. So what are the initial conditions given? So for the mass 1, when the time is 0, the displacement is 0. So similarly for the mass 2, when the time is 0, the displacement here is given as 0.004. Okay, so then the velocity when the time is 0 is 0. And for the second mass also the velocity when the time 0 is 0. So these are the initial conditions for the system. Okay, okay, so we assume the solution. Okay, now before that, so we can substitute. Okay, so substituting the given values. So that means the mass, stiffness, damping constant, and stiffness constant. So we can write the two equations of motion as 5x1 double dot. So plus 60 x1 dot minus 30 x2 dot. So plus 4000 x1 is equal to 0. So this will be the first equation of motion. Okay. So the second equation of motion will be 10x2 double dot. Okay. Then minus 30 x1 dot. This is the damping constant. So plus 30 x2. Just give me a minute. Let me check the given values again. Okay, M is 5 kg, C is 30 newtons second, 4K, so 4000 newtons. Okay, so the first equation is mx1 double dot plus 2c x1 dot minus c x2 dot plus kx1. Okay, is 0. So the second one is 2m x2 dot. So m is 5 kg, so 2m is 10. Minus c x1 dot minus 30 x1 dot. So plus c x2 dot. So you will have plus 30 x2 dot is equal to 0. All right. So we can write the two equations of motions like this. All right, guys. So I'll go back to the camera. Yeah, so these are the equations we can write. So now we need to find the response for this term. So we can assume a solution. So assuming a solution, so in the form, okay, so the two masses, so we can say the response of the two masses as x1 and x2. Okay, so we take as 1 and x exponential power lambda t. Okay, so now we need to substitute this x1, x2 values into the equation. So that means we need to take x1 dot, then we need to write down x1 double dot, then we need to write x2 dot, okay, this, and also x2 double dot. Okay, so x1 is simply 1 into e power lambda t. Then the derivative of x1 will be, so lambda into e power lambda t. So you need to just take x1 t as e power lambda t, x2 t as x into e power lambda t. Okay, so from here, then you take, okay, so you calculate x1 dot, so you calculate then x1 double dot. Okay, so similarly from here, calculate the first derivative, calculate the second derivative. So substitute these values in the given equations 1 and 2. Okay, so substituting x1 dot double dot, x1 dot, x2 double dot, and x2 dot values in equations 1 and 2. Okay, so you need to substitute whatever the values you get for x1 dot, x1 double dot. Okay, so substitute in these two equations and simplify. Okay, so you need to show in your assignment how you calculate x1 dot, x1 double dot, x2 dot, x2 double dot, then substitute the values here and simplify. So I give you the simplified values only, but you need to show all the steps. So you end up getting the two equations simplified versions as 5 lambda square. So plus 60 lambda minus 30 lambda x. So plus 4000 is 0. So this will be your first expression once you substitute the x1 dot, x2 dot, x1 double dot, x2 double dot values in the equation 1. So we call this as equation 3. So then the second equation becomes 10x lambda square minus 30 lambda plus 30 lambda x is 0. Okay, so your fourth equation will be like this. All right, so now to get a non-trivial solution. So one solution, easy solution is that lambda is 0. Okay, so to get a non-trivial solution, can I take out this paper? All right, so if you don't get a response, then I take out. All right, to get a non-trivial solution, equations 3 and 4. So you need to make the determinant of the coefficients to 0. Then here you get lambda square plus 30 lambda will be 0. Okay, so you can find the multiplication of this. So you can write 5 lambda square plus 60 lambda plus 4000 multiplied by lambda square plus 30 lambda. Okay, so this becomes minus of minus becomes plus minus. Okay, minus 30 lambda minus 30 lambda is equal to 0. Okay, so simplify this equation. So you get a fourth order equation. And solve it. Okay, so you may get a fourth order equation. Okay, so you will get four values for lambda. So you will get four values for lambda. Okay, so lambda 1, lambda 2, lambda 3, and lambda 4. Okay, so you may get some real values, some complex values. Okay, I think I'll stop here after that. So I showed you one of the example, so which is listed in your learning guide. All right, so the previous paper I can show. So Daryl, which part you want to see? Okay, so this is the bottom part. All right, Gauri, so you can see the top part. All right, so I'll stop the solution here. The rest of the part, so you just follow the example the same way, okay? And you may have to use, okay, probably some either MATLAB or Minitab or engineering equation solver to solve the 4x4 matrix. Okay, so I'll not give you all that, so you can work on that. All right. Uh, any questions? Let me know. Otherwise, I can talk something about your class tests on Sunday. So please note that don't forget your class test on Sunday, 3 to 4:30 p.m. Okay, I gave you 25% of the solution. So the rest of the solution you can work yourself. So based on the example which I showed you. Not this one. So you can follow this example. So whatever the example shown here is, okay, so this is the example. So you are given the uh, initial conditions, and then you got the system here. So in our case, we straight away got the equations. So this one we could get from the given data. So we applied this part, then you got this one, okay, the determinant. Then once you solve the determinant, okay, in your case, you'll get a fourth order determinant. So you get four values. Okay, lambda 1, lambda 2, lambda 3, lambda 4. So here also you have four values. Okay, so it's a complex conjugate. So the first value is plus, the second value is minus. So similarly here, the first value is negative 1.2378 plus 2.2648. The second value will be negative 1.2378 minus. So you will get the four lambda values. Then you just follow this example, okay? And yeah, it is exactly the similar working. So the final solution, so you may have to solve a 4 by 4 determinant here. So four simultaneous equations you get, and solve the coefficients A1, A2, A3, A4, and your final response you can write in this particular format. All right. So you have to just follow this example. That's all. So you may note down this example. Uh, yeah, this is only for assignment. Exams, you will not be asked this type of questions. Okay. So this is a damped free response system with initial conditions. So you need to find out the free response of the system, including the natural frequencies, mode shapes, etc. All right. Any other question, guys? All right. Okay. Okay, then I move on to the class test discussion. Okay, so for the class test discussion, just like you can't see the camera. Give me a minute, there's a problem, I think. Guys, can you hear me? Give me a minute. I think there's some problem with the camera. So what I do is I just log off and I log in again. Okay, so I would like to write the relevant formulas for them. Give me just a couple of minutes. Never mind. Never mind. I'll go through the slides. Okay, it is the same stuff. Instead of writing, then I can use the same thing. Guys, can you hear me now? All right. So, so can you see the slides? All right. So let us just it goes as a review for the midterm online class test for the Sunday. Okay. Uh, to say there will be 4 questions. Okay. The question paper consists of 4 questions. So each question will have 25 marks. Yeah, all right, Shafiq, I'll record now. So there will be 4 questions, and each question will have 25 marks each. Okay, the first question will have uh, so 10 MCQ questions. So multiple choice questions. Okay, So you need to answer the questions in alphabetical form. Okay. So answer all questions showing your numerical calculations. So you need to show your calculations, okay, for all the 10 MCQ questions. So this MCQ questions would be simple, quite simple in the sense you will have mass given, stiffness constant given, then you will be asked to calculate what will be the natural frequency. So you can just simply calculate omega n as square root of k by m. So all the 10 MCQ questions, you will have the required information. Then you need to just answer the questions in uh, and show your small calculations, all the calculations for the 10 questions. So these 10 questions will be can be completed in 15-20 minutes. So you don't need much time to solve these MCQ questions. But the answers will be provided also. So you need to pick up the right answer and you need to show how you got the right answer. Okay, that is the first part of the question. So the second part of the question, you will have to answer the second question. You have to draw the free body diagram and you have to do the energy method and derive equation of motion. Okay, I just type here Q2 is the question 2 is use energy or Newton's method and derive equation of motion. So for this question, depending on what is asked, you need to draw a free body diagram and the derivation should be step by step, and you may have to find the natural frequency of the system also. Okay, so this will be the question 2, and question 3 will be related to the mass and spring system. Okay, so where you need to get the response, so free vibration response of the system. So Q3 will be so free vibration. You need to all the relevant data will be given. So in the form of a equation, then you need to solve the equation for the response of the system. So we have done some questions related to that, and you have also done questions related to this in your first assignment. Okay, so then the question 4 will be so we'll have forced vibration. With amplitude transmissibility. Okay, so related to amplitude transmissibility or the force transmissibility issues. So you must have done similar questions in the assignment and also during the sessions. So the 4 questions you have to complete in 1 hour 30 minutes, and yeah, you need to upload your answers. So always you get good marks if your working is okay, all the steps, okay, you need to show all your steps, all the working, and you always highlight your final answers, okay, and wherever required you need to draw the free body diagram, okay, and wherever you need to do the derivations including the differentiation, you need to show. All right, question 2, 3, 4 can be done in less than. So each question may take 10-15 minutes. So in general, all the 4 questions can be completed in an hour. So you will have still some time to verify your answers and also to upload, scan and upload. All right, so your exam, I think you can start downloading the question paper at 3 p.m. Then upload by 4:30 p.m. All right, so would you like to ask anything related to the class test? Otherwise, so what is question 4? Oh, you can't see what is the question for? Can you see now? All right. One suggestion is that you guys, because you are doing online, not a supervised exam, okay, you guys can share your final answers or some, how you can work out, but don't share your complete workings. So that way, actually, if you share, you are going to lose your marks with others. So we can easily find out if any shared answers, and normally the impression goes down. All right. So, but you can discuss for knowledge purposes, but when you work out, do your own way. All right, guys. Any other questions you have related to the class test, online class test? I think probably this will be the last time you will be doing online exams. From next term onwards, I think everything will be supervised. Uh, any questions or any doubts, any other information you want, let me know. Any questions? Then I'll just go through the revision and let us do some exam related questions. So for the end of term exams, there will be 5 or 6 questions. Okay. So 3 or 4 questions will be from the single degree of freedom systems, and 2 questions will be from multi-degree freedom systems. So guys, can someone respond? Today is our last class. Yes, no, Razar. Uh, Azhar, yes, today is our last session. Of course, you will be having pre-exam workshops by Professor Fahd. I'm not too sure when, but I think the school must have communicated with you. So I think he may be coming down. I'm not sure. So can you update me on that if you know any information? When is your pre-exam workshop? Anyone? 16 to 18th March or April. Oh, March. All right. 16th to 18th March. All right. All right. So Professor Prasad will again go through all the relevant stuff, and also we'll go through some um, exam questions, and also some give you the structure of the question paper, etc. But I would like to add to that that normally for the end of term examinations, I hope all of you are listening carefully. So for the end of term examinations, you may not get uh, the unique question paper. So the questions will be randomly generated to you. So from a pool of, every question will have 3 or 4 different questions. So altogether there will be 30 questions, and you may get 6 questions from the pool of 30 questions. So once you log in, you download, okay, don't change your questions. So you just follow, okay. So if you log in again, I think your questions will change. So there will be a problem like that. So you will have only one chance to log in, and that will give you a set of questions, and you need to stick to the same set of questions. All right, so the questions you will be getting may be different. Each one may get a different set of questions. Some questions may be common, but some questions will be definitely different. If you answer any question that is not given to you, so you may get no marks for that question. Is that clear, guys? So you will get a question paper customized to you. So from randomly selected questions. But of course, the questions 4 from single degree freedom system and 2 from multi-degree freedom system, so that consistency will be maintained. So only thing is you may get different questions. Each one may get different type of questions. Is that clear? Can run through some of the questions for the online test. You mean for the class test? Class test is, don't worry, it is going to be simple. And of course, the most important part is you need to know the relevant equations to use, so relevant formulas to use. So that is important. All right, so I'll be going through some of the relevant questions definitely, but it won't be like the solid mechanics paper. Okay, so this exam will be slightly different compared to solid mechanics. So I clear this, then let us move forward. Okay, so what I'm going to do for the next till we have a break time, and after break will be a revision, and also we do something related to not only your class test but also for the end of term exam. All right, so the first thing is okay, first thing you can focus on the slides. Unfortunately I can't right now. Okay, so you have a mass and spring system, right? Okay, so we ignore the friction, so we only consider the damping friction due to non-viscous forces. Okay, so therefore we can ignore the frictional forces when we discuss the mechanical vibration system. So for a simple spring and mass system, so you can write the Newton's law as the net force acting on the mass is equal to the spring force. So this will be your equation of motion for this. So the right hand side is 0 because we do not have any external force. Okay. So this is a second order differential equation because x double dot is the second order differential. Okay, so if you know the initial conditions, means what is the displacement when time is 0, Okay, so let us say x naught when the displacement when the time is 0, and let us say the velocity when the time t is 0 is v naught. So the solution of this equation, okay, we look into that solution. So for this, the spring force is minus kx. So the time within the bracket is just a variable. So sometimes we just write minus kx. Okay, so the time within the brackets indicates that the displacement x varies with respect to time. Okay, so the mass, the initial force is ma. So you can also write mx double dot. Okay, the same thing when you're dealing with a rotational motion, for example, for pendulum. So you have angular displacement theta. So, and here for pendulum is subjected to gravitational force. Okay, so the equation of motion for this will be theta double dot plus g by l, theta is equal to 0. Okay, so the same equation of motion considering the moment of inertia. So if you have a torsional disk like this, so the equation of motion for this system will be uh, J. J gives you the moment of inertia. So depending on the shape of the, the system, whether it's a link or a rectangle, so the mass moment of inertia can be taken from geometric properties. So normally in mechanical vibration course, the J value, that is the moment of inertia value, will be given along with the question. Okay, so this slide basically tells you that for different types of single degree freedom systems, okay, how to write the equation of motion. So the equation of motion corresponds to the second degree of freedom, second order differential equation. So since the right hand side is 0, so these are called the second order homogeneous differential equation. Okay, so the solution of this second order differential equations so you can write it as xt is equal to a sine omega nt plus phi. So this is the standard form. It's a harmonic function. So the displacement also varies as a harmonic function. So we include a sine or cosine function, so to indicate the solution. So now we take the derivative of this x dot t. Okay. So when you take the sine theta, the derivative becomes cosine theta. But since you have omega n, so omega n comes out of the sine theta. So the derivative of xt will be omega n a cos omega n t plus phi. So this is the first derivative of this. Then the second derivative, if you further differentiate this, so you get the second derivative. So second derivative cos omega n t becomes minus omega n sine omega t. So this becomes minus omega n square. Okay, so a sine omega nt plus phi. So you know this a sine omega nt plus phi is nothing but x again. So this is equivalent to again the displacement. Okay, so therefore you can also write x double dot t as minus omega n square x. Okay, so now substitute these values into the equation. Okay, the equation is this. So we need to substitute in the first equation. So which is in this equation. Okay, the equation of motion. So then you can write down this. Okay, so you get minus m x double dot. Okay, so x double dot is m into x double dot plus k into x is equal to 0. So from this you can write minus omega n square plus k is equal to 0 because you can cancel out this. Okay, so a sine omega nt plus phi. So from here, you can show that the natural frequency of the system is square root of k by m. Okay, so you may be using this formula to calculate the natural frequency of the system. So when you know the stiffness constant and mass m. Okay. So basically in simple harmonic motion, so is th- this example defines the period. So what is the period of the vibration? So the period of the vibration gives you the time taken for one complete oscillation. So the time taken for one complete oscillation. So if the vibration, the maximum amplitude is here, then it goes down and comes back to the same level. So this is the time taken to complete one oscillation or one vibration. So the period is defined as 2 pi over the natural frequency. Okay, then the frequency natural, okay, in hertz. So you can see that the frequency is expressed in two ways. One is the frequency in hertz. Okay, so that means it is simply the number of oscillations per second. So how many oscillations per second? That is the frequency. So you can also refer to the radial frequency or the circular frequency in radians per second. Okay, so if you multiply this f with the 2 pi, so you will get the circular frequency or the radial frequency, 2 pi f. Okay, so the unit for this will be the radians per second. So we also call this as angular velocity also. So this is how the angular displacement varies with respect to time. Now, guys, what is the relationship between the frequency f and the period t? So how they are related? Anyone? So period is time, frequency is the number of oscillations in a second. So the anyone? Yeah, it is the inverse relationship. So the period is can be given as 1 over f. Okay, so the first question, probably you need to know all these things for calculations. So the MCQ question, so you may be asked to calculate the frequency, you may be asked to calculate the radial frequency, natural frequency, then you may be asked to calculate the damped natural frequency. All the data will be there. Then the period of oscillation. Okay, so you may require all these formulas. Okay, so when the initial conditions are there, so when you know initial conditions refers to what will be the displacement when the time is 0 and what will be the velocity when the time is 0. So if you know these two conditions, then you'll be able to use these conditions and solve the response of the system. Okay, suppose if you know the initial conditions, let us say, okay, so you know what is the displacement when time is 0. So you can substitute this in the expression here, and you can write this as a sine phi, and again the velocity, the derivative of this. So it becomes omega n into a cos phi. So if you know the initial conditions, so you can calculate the amplitude using this formula and the phase using this formula. Okay, so you may note down these equations also. So here x naught is the initial displacement, p naught is the initial velocity. So these are the initial conditions. So x, yeah, only these two things. So don't get confused. We also write v naught as x dot All right. Guys, I think now the time is nearing 8:30. Let's go for a break and let us meet. So let us meet at 8:50. Is that okay? So we'll go for a break now. After the break, I'll go through some more things, particularly touch upon the relevant equations needed, not only for the class test, but also for the end of term exams. All right. Hi guys, hope you're back. All right. All right. Yeah. Okay. All right, guys. Then we'll start. I start regarding the session. So now the final response of the system can be given like this. So this is, we call it as the solution for the simple harmonic oscillator, or the simply the mass and spring system. So here, this one basically tells you for any time, the displacement of the system can be given in terms of the natural frequency and in terms of the time. So how the time varies, then the displacement of the mass varies. So this is the response of the system. So here, yeah, you are simply writing this as A sine omega n t. Okay, plus phi. Okay, now you know the value of A, you know the value of phi. Okay, so A is nothing but the whole thing, amplitude. So sine omega n t, and phi is written as tan inverse of the whole thing. So the whole thing is nothing but the phase. All right, so you can write the response of the system xt like this. So then for the first question I was referring, probably you may require formulas like this. The period you can calculate as 2 pi over a radial frequency. Okay, then the natural frequency of the system in hertz, okay, you can write it as omega n over 2 pi. Okay, when you're dealing with the pendulum system, okay, the natural frequency of the system is root g over L. Okay, then the period of the pendulum can be 2 pi root L over g. So because period is 2 pi over omega n. Okay, omega n is replaced with root g by L. So you can write the period of the vibration as 2 pi root L over g for the pendulum. Now the same thing for a disc and shaft, you can write the natural frequency of the system is for the disk. Instead of mass is replaced with the mass moment of inertia. So square root of k over mass moment of inertia. Okay, so then you can write the period as 2 pi root j over k. So this is for the disk and shaft, and the top one is for the pendulum. So you may note down some of these formulas. Okay. What is the relationship between displacement, velocity, and acceleration? Okay. So, you know, when you write displacement as a sine omega t plus phi, okay, the derivative of this gives you the velocity. So velocity will be omega n into a cos omega nt plus phi. Then the second derivative is like this. If you see in graphical format, so when the displacement is maximum, okay, so acceleration will be negative maximum. You can see the acceleration is negative maximum. Here, this is positive maximum. Here, it is negative maximum. So here you can see the amplitude is negative maximum. Then for the velocity, this will be positive maximum. So you can see the displacement and acceleration, they actually will be opposite in nature with respect to time. Okay, so that is the relationship between displacement and acceleration. So you can simply write this as negative omega square into x. All right, so I just leave this. Then uh, mathematically, when we write the solution for the mass and damper system, okay, uh, when we write x is a sine omega t plus phi or omega n t plus phi. Okay, so this solution we call it as the magnitude and phase form. So A basically is the amplitude or the magnitude. So this is the maximum displacement. And phi is the phase. We can also write the solution mathematically the same. The first one and the second one and the third one all are same. So we can also write in terms of a sine and cosine function. So this is called the Cartesian form of the solution. So here A1, A2 are the constants. So you are representing both the sine harmonic function and cosine harmonic function. Okay, so this equation 1, equation 2, and equation 3 all are same. So mathematically, there's no difference in among the three equations. So you can also write in a polar form. So exponential power a1 into exponential power I omega nt plus a2 exponential power minus I omega nt. So a1, a2 will be the constant. So we can represent this response of the system in either format. Okay, in either format. So mathematically, all these equations are the same. And in the beginning of the session, when we had the first session and second session, I touched upon these things. All right. So next we introduce the damper into the system. So when we introduce the damper into the system, so now you have mass, the stiffness constant, and also the damping constant. So in this case, the equation of motion becomes mx double dot plus cx dot plus kx is equal to 0. So this is again a free response with a damper. So damped free response because external force is not facilitating the vibration. So this is the equation of motion. So now when we deal with the damper, okay, what happens is the most important part of this is, okay, you deal with the damping ratio eta. So eta comes into picture. So what is eta? Eta is the damping constant C over the critical damping constant C. So, because this damper acts in a way to reduce the vibration, but depending on the damping ratio here eta, so sometimes the system may not give any vibration at all. Okay, that means it is over damped. Critically damped also there is no vibration. Only in under damped cases, so you will have vibration. So we'll study the response of the system, okay, in terms of this damping constant. So this, whenever you are studying the expressions, including the damping for the single degree of freedom system, so we will be using this damping constant. Okay, for the first question, you will be calculating this damping ratio. So you'll be calculating the frequency, you'll be calculating the period, you will be calculating the damping constant also. Okay, so the damping constant you can write, damping ratio, we can write it as C over the critical damping constant. Now the critical damping constant is, 2 square root of Km. Okay, when eta is 1, okay, the damping ratio is 1, so this C is equal to critical damping. So we can write now the critical damping as 2 square root of Km. You can also write it as 2m omega n. Okay, so when the damping ratio is less than 1, so the system is called underdamped, right? When the system is underdamped, then you can calculate the damped natural frequency of the system, omega d. Okay, so for the first question, you will be using this formula also. So the damped natural frequency of the system is omega n into square root of 1 minus eta square. So you will have all the information to calculate eta, then critical damping constant, then the damped natural frequency of the system. All right, so for the first question, all these equations are required. So the initial conditions, as we have done earlier, so the magnitude of the vibration and phase of the vibration can be calculated once you know the initial condition. So initial condition always refers to when the time is 0, so what will be the displacement and what will be the velocity. Okay, when you have this x naught is the initial displacement. Okay, so v naught is the initial velocity. So once you know these two things, okay, once you know these two things, then you can calculate the amplitude of the vibration, and also you can calculate the phase of the vibration for the underdamped case, when the damping ratio is less than 1. So when eta is less than 1. Okay, only when eta is less than 1, you can have a damped vibration like this. Okay, so natural vibration is omega n. So then the damped natural vibration is omega d. So there's a relationship between these two. So omega d can be written as omega n into square root of 1 minus eta square. Okay, so make sure to prepare your own formula sheet, for readily using during class test. It really saves your time. So instead of looking for each formula separately, so make sure all your formulas are in 1 or 2 papers. So therefore you can readily use and save your time. This exam, no formulas will be given even for the end of the term exams. So no formula sheet. So normally during the supervised exams, we will allow you to carry one A4 size formula sheet, handwritten. So, but now because of the online systems, you need to prepare your own formula. All right, so for solid mechanics, yes, the formula sheet will be provided, but not for mechanical vibrations. All right, so the next we'll see the modeling and energy methods. So modeling is required uh, to derive the equations of motion, so particularly using energy method. So we can also derive equations of motion not only from the Newton's method, but also by calculating the total energy in the system and taking the derivative of the energy and equating it to 0. So we'll be able to find the equations of motion. So your second question, guys, you're listening, right? So your second question related to the derivation of equation of motion of the given system. So, and you'll also be asked to write down what is the potential energy in the system and what will be the kinetic energy in the system. So, um, probably you can also draw your free body diagram and derive the equation of motion of the system. Not only derivation of equation of the motion of the system, but also you need to find an expression for the natural frequency of the system. So the formula for the natural frequency of the system. Okay, so this is related to the second question. So deriving an equation of motion and expression for the natural frequency of the system, and also calculating the potential energy and kinetic energy in the system. Now, for a simple mass and spin system, you know the potential energy is half k x naught square. Okay, so yeah, you've done this expression in your engineering dynamics course, right? So I need not explain this. So then the kinetic energy due to the linear motion. So the translatory kinetic energy is half m into v square. Okay, so this is for a linear motion. So when the mass is having movement along horizontal axis along x. Okay, so the same rotational kinetic energy. Okay, so the mass is replaced with the mass moment of inertia. So mass per rotation becomes mass moment of inertia. So the symbol is used J, but I think in engineering dynamics you might have used I. So it, some courses they use mass moment of inertia J, and in some books they use as I. So you need to get familiarity with both. So the x dot, the linear velocity, is replaced with angular velocity theta dot. So when we say angular velocity, this is simply your circular frequency, radial frequency omega. So this is also known as angular velocity. So this is the rotational kinetic energy of the system. So you need to analyze the given system, whether is there any motion that can be, if there is an angular motion, you can always convert the angular motion into linear motion. So you know the relationship between angular variables and linear variables. So if you have the linear motion, x is the displacement, and for angular motion, theta is angular displacement. Okay, linear velocity is v r x dot. Okay, angular velocity will be omega r theta dot. So what is the relationship? So you can say that v is equal to r into omega. So r is the distance, depending on the axis of rotation. So you can define, sometimes it can be length, sometimes it can be equivalent to radius, sometimes it can be the height of the system. So r is basically, it connects from the centroid of the rotational axis to the point where we are calculating the velocity. So similarly, A can be angular linear acceleration. So we write alpha, angular acceleration. So we know that A can be written as r into alpha. So alpha is also theta double dot. So omega is theta dot. So alpha is theta double dot. So like this, the mass is replaced for linear motion. For rotation, mass is replaced with mass moment of inertia, J. So similarly, you have potential energy, okay, and for rotation, you have half J into omega square, rotational kinetic energy. Okay, so we know the law of conservation of energy. So the law of conservation of energy tells us when a system undergoes a change, okay, from one state to another state, so the total energy in the system is constant. So the total energy in the system is constant when the system undergoes a change. So that means the time derivative of the total energy must be constant. So that means the total energy, there's no change in the total energy when the system undergoes a change. So that means the time derivative of the total energy is equivalent to 0. So this is precisely formula which we will be using to derive the equations of motion from the systems. So, for example, if you have a mass and spring system like this, so you can write what is the total potential kinetic energy and potential energy in the system. So this is a very simple example. So the kinetic energy is half mv square. The potential energy in the spring is half k x square. So this is the total energy, and we are taking the time derivative of that and equating to 0. So once you do this derivation, you will get back the equation of motion for the system. So this is how you can derive the equation of motion of the system using energy method. So your second question, probably you will be asked to derive the equation of motion using both the Newton's method and also the energy method. So probably you will be having a simple mass and spring system, okay? And for that you need to derive the equation of motion and also derive the natural frequency of the system. So in this case, so you know that the potential energy, the maximum potential energy and maximum kinetic energy, they must be equal. So you can write half k square will be half m into omega n a square. So you can easily prove that omega n, the natural frequency of the system, is square root of k by m. Okay, you can also prove this from the other methods. Okay, so this is your Leningrad example. So you have a mass and spring system connected to a disk. Okay, so the disk has both the angular displacement and also the linear movement. Okay, so for this we can write the rotational kinetic energy is half j omega square. Omega is theta dot square. Then the translatory kinetic energy is half m x dot square. Okay, so here, okay, your second question will be definitely there will be a spring and mass system attached. Okay, so this example can be of some help for you. So you can relate the linear and angular variables. So you can write x is equal to r into theta. So then x dot is r into theta dot. So the rotational kinetic energy, then you can write half I omega square. Okay, so omega can be written as, okay, r into omega. So r into, so v is equal to r omega. Okay, here you will have half I omega square. Rotational kinetic energy is half j omega square. So instead of half mv square, so you have half m omega square. So omega square can be written as, okay, v is equal to r omega. So we can write v square is r square omega square. Okay, so the maximum rotational kinetic energy, so you can write as half I. Okay, so the maximum velocity is replaced with omega n into a. So this part we have seen that, okay, the maximum velocity will be when you have cos omega and t. So the maximum velocity occurs when cos theta is 0. So when cos theta is 0, so this value will be 1. So the maximum value for this will be 1. So therefore the maximum velocity will be omega n into a. So the maximum translatory kinetic energy you can write in this way. So this is the rotational kinetic energy plus the linear kinetic energy, translatory kinetic energy. So you can add these two things, so then the maximum kinetic energy you can write in this particular way. Okay, so then the maximum potential energy is in the spring. So you can write this as the maximum potential energy. So then you take the time derivative of these things. Okay, you can write the equation of motion uh, like this, and from there you can write the natural frequency of the system. So to write the natural frequency of the system, always you need to compare the system with your equation of motion. So m x dot square plus kx is equal to 0. So omega n, you write it as k by m square root. So write your equation of motion in the standard format like this, and from there you'll be able to find out the natural frequency of the system. Okay, so you can also go through the learning guide for a more detailed explanation of this. Okay, so the next thing is mass and spring system. Okay, where there is a force acting on the system. Okay, so this is a without a damper, so it is an undamped forced vibration. Okay, so we choose the force as also a harmonic function. So that means the force will also have a magnitude of f naught. Okay, and also force is having a frequency omega. So this is also known as the driving frequency. Okay, so in this case there is no damper, so C is equal to 0. So the analysis of the system, you can just follow the learning guide. So we have the damped forced vibration like this. So we choose. So then the equation of the motion for this will be, we can derive from the Newton's law. Okay, so y double dash plus k by m into y is equal to f naught sine omega t. Okay, so then in this case, this is a second order differential equation. Okay, and the right hand side is not zero. Okay, so it is a non-linear second order differential equation. So the solution of this equation will have two components. So the solution y can be written as a y complementary functions, which we derive by taking the right hand side as 0. Then a particular part of the solution yp. Okay, so these two forms we can. Okay, so there are two forms of this solution, the particular solution and the complementary function. So you can write the complete solution for this, okay, in this form. So YC we are now writing as in Cartesian form, A sine omega nt plus B cos omega nt. So this solution is coming from the particular solution YP. Okay, so you can see that now the solution has two parts. Okay, so this is the response of the general solution for a mass and spring system with external frequency omega. So here, this part is important, omega over omega n. So omega over omega n, we call it as the ratio of the frequencies R. Okay. So this one is just a number, no units for this. So this play a, an important role in analyzing the systems related with forces. So when the systems are uh, acted upon by external forces, then this R comes into picture in most of the equations. So here the omega refers to the excitation frequency or the frequency of the force. Force frequency. Omega n is the natural frequency of the system. Okay. So next we can study the equation of motion for the damped and forced vibration. So we can see damped system under a harmonic force. So this is the equation of motion for a damped system under harmonic motion. So again, this system will have two solutions, the complementary solution and particular solution. So we can write the two forms here. Okay, so the particular solution we can write in this way. Okay, so here the displacement of the system x can be, you can calculate from this expression, or you can calculate from this. Okay, so for the, here we are going to define the magnification factor or the amp. Okay, so this formula is where you are taking the ratio of the displacement and the displacement due to the spring. So the ratio of two displacements. So this one we normally call it as the magnification factor. So the displacement, we know that force can be written as kx. Okay, so force over k is basically the displacement of the spring. So capital X is the displacement of the mass. So the ratio of these two things, we can call it as the magnification factor. So you can write the magnification factor as x, capital X is the amplitude of the displacement, k over f naught. So this is your expression where omega over omega n you can replace with r. So omega over omega n you can replace with r. So similarly, the phase can be calculated from this. So this equation, you can simply write it as 2 eta r over 1 minus r square. Okay, your fourth question may be related to this. Okay, where you will be calculating the magnification factor and where you will be using these equations. Okay, so all these things are related to your class test. All right, so I'll just, because this forced vibration is also related to base excitation, and we can talk about the force transmissibility. But before that, how this amplitude varies with respect to the ratio of frequencies, omega over omega n. Okay. So you can see that when omega over omega n is equals to 1, so you can see the amplitude of the vibration maximizes. Okay. So when omega is equal to omega n, r is 1. Okay. So guys, can you tell what is this condition when r is equal to 1? So that means the excitation frequency equals the natural frequency. So this condition is called, we use a particular word to refer this condition. Uh, can you tell what is this condition is called? That's correct, C.D. Chen. So this condition is called resonance. So when you're asked to calculate what will be the resonance frequency, okay? So resonance frequency means your natural frequency should equal to the resonance excitation frequency. Okay, so please note that there will be a small MCQ question where normally the students tend to pick up a wrong answer. That is mainly because they are not sure what is resonance frequency. So resonance frequency means it is the equivalent to the natural frequency. So when the question asks you what is the resonance frequency, you will be wondering what equation you need to use. But simply your natural frequency is equal to the resonance frequency. So when the excitation frequency equals to the natural frequency, then the resonance conditions take place. So during resonance, the amplification, the magnitude of the vibration becomes maximum. All right, so this is the phase plot. Again, you can see there is a phase variation when during resonance conditions. Okay, so the base excitation is part of the forced vibration, because when the base is excited, so we can consider the magnitude of the base excitation as part of forced vibration. Okay, so this is also included in your class test. So the magnitude of the base excitation can be, uh, this is the equation of motion for the base excitation. So here there will be two displacements. One is the displacement of the mass, capital X. So this will be the amplitude of the um, displacement for mass, and base excitation, base amplitude, you can call it as Y. Okay, so when we analyze the situation, then we'll have this amplitude ratio. Okay, this is also called as the force transmissibility. Okay, so both are equal, amplitude ratio or force transmissibility. So you please take note, you may be using this expression for the fourth question. Okay, so you can either use this expression or the bottom expression, both will be the same. And the force transmissibility and displacement transmissibility, both will be the same. All right. So there will be many other things, but your class test is included up to this point. Then what I do is I go through some questions. You may try to work those things. All right. So look at this example. So guys, try to do the calculation. So the mass of the locomotive car is given 4,000 kilograms. So it is traveling at a velocity of 10 meters per second. So this is stopped at the end of the tracks by a spring damped system. Okay. So if the stiffness of the spring is 40 Newton per mm, okay, and the damping constant is 20 Newton second per mm. So this is the C value, K value, M value. So velocity is given. Okay. So the first thing is calculate the natural frequency of the system. And the spring damper system in radians per second. Guys, can you calculate and let me know your answer? Omega n is square root of K by M. So any answer? Notice that I think I said the answer is not correct. So K is 40 Newton per mm. Okay, so in terms of newtons per meter, what will be the value? So K will be 40,000 Newton per meter. So you need to multiply with 1,000 to convert this into Newton per meter. So you need to make sure that the units must be the same. So 40,000 mass, you can take it as 4,000. So guys, anyone? Yeah, I think the answer should be 3.16 radians per second. So Safaruddin has given 3.16, so the unit should be 3.16 radians per second. So then calculate number 2. So the answer will be 3.16. So please note, if you don't write the units, there will be some penalty. A small portion of the marks will be reduced. Then calculate the damping ratio. So what is eta? So to calculate the damping ratio, you need to calculate the critical damping constant. So the critical damping constant will be 2 root km. Okay, so then you can calculate eta is equal to C over Cc. So guys, you can tell me what is the critical damping constant first. So give me this value first, followed by the damping ratio. 25298 is correct. So then damping ratio. So during the exams, you need to give the unit also. So you need to say Newton second per meter. So what about the damping ratio? So you know the C value, that's right, 0.791 or 79, both are okay. So you need to be careful because here the unit is given Newton second per mm. So to get the ratio, you must also multiply this with 1000. All right, so then the third part of the question is the damped natural frequency of the system in radians per second. So third, so calculate what will be the damped natural frequency. So for the third one, so you can write to omega d is equal to omega n into 1 minus zeta square under square root. So any answer for this? So 1.937 is correct, Shafruddin, radians per second. So 1.937 radians per second. Then you can try number 4. The period of damped vibration. So the period, you can write it as so this is 2 pi over natural frequency, damped natural frequency, omega d. Yeah, guys, any answer for part 4, the period of damped vibration? That's correct, Michael. So that is 3.245 seconds. So then you can calculate the maximum displacement of the car after engaging the spring, okay, and the damper. Okay, so the maximum displacement of the car means you need to find the response x. So to calculate the response of the system, so you need to know how to write the response of the system. So the response of the system, you can write it as x is equal to, for the given system, exponential power. Okay, I'll write in the next slide. So we can write the response of the system, x is equal to exponential power minus eta omega nt okay, multiplied by, so a cos, sorry, so a cos omega dt plus b sine omega dt. So there are different ways you can write. So either you can write like this, okay. So omega d you can replace with omega n into, so omega d can be replaced with omega n into 1 minus zeta square square root. So it doesn't matter. So, but the initial conditions are given. So, what are the initial conditions? When time is equal to 0, when time is equal to 0, so the displacement is given as 0. X naught is given as 0, and the velocity is given as 10 meters per second. So the velocity is given as 10 meter per second. So these are the two initial conditions given in the description of the problem. So these are given. So you can pick up these things from the description of the problem. Okay, so now substitute these values into the equation and solve. So to substitute these values, okay, so first you can substitute x is equal to 0. Okay, when time t is 0, so x naught is 0. So when you substitute the first one, so first initial condition, so you can say 0 is equal to, okay, so when time is 0 here, so the whole thing is 0. So e power minus 0, okay, then a, then cosine omega dt, okay. So t is 0, therefore the whole thing will be 0. So you will have a into cos 0, okay. So plus b sine 0. So this is by substituting the displacement is 0 when the time is 0. Okay, so from this, anything to the power of 0 is 1. So cos 0 is 1. So sine 0 is 0. So this means that a is equal to 0. Okay, so this is substituting that the time is 0, displacement is 0. So now this is x, right? So find the derivative of this. So find the derivative of x dot. So x dot expression is, so you have to take the derivative of this dx over dt. Okay. So when you take the derivative of this, okay, so exponential power of x derivative is exponential power of x. So you can just write this as exponential power minus eta omega nt. Okay, so here a cos omega t becomes omega into minus a sine. So I just take a bracket. So here omega d comes out. Then a cos omega t becomes minus, so minus a sine omega dt. Okay, so here cos omega t, you can simply write b cos omega dt. So sine becomes positive cos. So omega t we have omega d we have already taken as a common factor here. So here we need to do the uh, product rule. So this is one, so this is another variable. So two variables. So when you take the derivative of a product, so x into differentiation of this, then plus you need to take the function and take the derivative of this. Okay, so the derivative of this will be e power So you can write it as eta omega n, then multiplied by, so you can just write a cos omega dt plus b sine omega dt. So this is the total derivation of the given x value. So we'll be applying the product rule. So I need to put a flower bracket here. So that means this exponential power eta omega and t is a multiplication factor for the everything inside. Okay. So now we replace x dot with 10. Okay. And we put in this expression wherever t is as 0. Okay. So the first one we can write e power 0. Okay. So then we take the flower bracket, omega d we can write as it is. Okay. So a is sine 0. So sine 0 is 0. So the whole thing we just write a sine 0. So plus b cos 0. Okay. So then eta omega n we write as it is. Then we can write a cos 0 or plus b sine 0. Okay, so you will get this expression. So from this, okay, so this is sine 0 is 0. So of course, I didn't write the negative sign here. So add the negative sign here. So when you simplify this expression, okay, I just to take out this. Okay, when you simplify this expression, so this 10 becomes, okay, so exponential power 0 is 1, anything to the power of 0 is 1. So this one becomes 0, sine 0 is 0, so cos 0 is 1, so it becomes b. So the whole thing becomes b into omega d. Okay, so here cos 0 is 1, so sine 0 is 0. So minus eta into omega n. So from this you can calculate, because we know omega d, then you can calculate b value. So substitute this b value and a value in this equation. So substitute here a value and b value. So once you substitute then you'll be able to calculate you'll be able to give the response of the system. So that is the fifth question, right? Fifth part of the question. Okay, so you can give the response once you substitute A value and B value in the equation. All right. So this is okay. This example may be similar to your first question, and also may be similar to the third question. So a part of the question will be equivalent to the first question, and part will be equivalent to the third question. What would be the t is equal to t naught? Oh, t naught in this case is the initial time, right? So initial time will be 0. So the time taken to reach the maximum displacement. You are asking which one, Michael? The part 6? So when x maximum, then you have to calculate the time from x maximum. Yeah, the maximum displacement of the car is the in terms of uh, so you can write a value and b value, substitute here. So that will be your response. You can also use any other different formulas, including the phase angle also. Okay, so because you mentioned phase angle, then I'll move to another question where you will be using the phase angle calculation. So you guys can, there are many examples for you to work on here. So you can, yeah, either one will get the very similar answers. So now let us look at this example here. So a 25 newtons weight is, here Newton's weight is suspended from a spring, so which has a stiffness of 4.42 newtons per meter. Okay, the weight is given. The weight given an upward velocity of 5 meters per second. So when it is 40 mm above its equilibrium position, so this is the displacement given. Okay, so that means from the given description here, so you can say when t is equal to 0, so you can say when t is equal to 0, okay, so you can say the displacement x is equal to 40 mm, so you can convert into meters, so 0.04 meters. This is the initial condition, and the velocity is 5 meters per second. So you can also say that velocity v. So v is x dot, right? So we can write v is equal to of 5 meter per second. So these are the initial conditions for given based on the description for this problem. Okay, when time is 0, the displacement is given as 40 mm. That means 0.04 meters, and the velocity is upward velocity is 5 meter per second. So it is upward velocity, so you can take the velocity with a negative sign. So you can consider v as, so x dot 0 is negative 5 meter per second. Okay. So what is given? The weight is given as 25 newtons. Mg is 25 newtons. So from this, then you can calculate what will be the mass. So mass of the system you can calculate. So K is given as 0.42 Newton per mm. So you can convert into newtons per meter by multiplying with 1000. So if you multiply with 1000, then you get 420. Okay, so all this information you can get. So the mass will be equal into 25 over 9.81. So you will get the mass as 2.55 kilograms. All right, so you can get all this data from the given description. Okay. So then we can write the solution, the general solution we can write. So we can write that x is a sine omega nt plus phi. Okay, so when t is equal to 0, we know when t is equal to 0, oh, x is 0.04, right? Okay, so you can write a sine 0 plus phi. So a sine 0 is 0, so we can simply write this as a sine phi. Okay, so here the displacement is also what it says above its equilibrium position. So we can take for the displacement also with a negative sign. So I didn't add the negative sign here. So the displacement is negative 0.04. Then, yeah, the velocity is also negative. Okay. So now we can write this is equivalent to negative 0.04. Okay. So similarly, you need to differentiate this to get x dot. So x dot is, so you can write this as omega n into a, then cos, sine becomes cos. So omega n t plus phi. Okay. So when t is equal to 0, when time t is equal to 0, okay, x dot is given as -5. So we write -5 meters per second. Okay. So we can write omega n into a. Cos 0 is 1, so into cos phi. So you can write cos phi. So from this you can see omega n a cos phi is -5 and a sin phi is -0.04. Okay, so if you take the ratio of these two equations, so 1 and 2, so this is just to solve whatever possible here. So a sin phi over a omega n cos phi. Okay, so you can cancel a. Okay, so this you get negative 0.04 over negative 0. Okay, -5. Okay, so sin phi over cos phi is tan phi. So you can write this as tan phi is equivalent to, so we can write 0.04 over 5. So that will give you 0.08. So you can write tan phi is equal to 0.08 into omega n. So, but you can calculate omega n because we know the k and mass. So we can calculate omega n is equal to square root of k by m. So k, we got it as 420. And mass is 2.55. So if you do this calculation, how much you will get? Yeah, 12.83. So 12.83 radians per second, that's correct. Then from equation 3, you can call this as equation 3. Okay. So from equation 3, you can calculate 5. So phi is equal to, so tan inverse of So 0.08 into 12.83. So you can calculate the phi now. So let me know what will be your value. Uh, 45.75 degrees, convert into radians. Oh, I'm sorry, I think this is 0.008, right? So there will be two zeros here. I think check your calculation. So this should be 0.008. This ratio 0.04 or 5 is 0.008, right? So this will be 0.008. So can you redo your calculations? Just hold on. What's that answer? 5.86 degrees. That appears to be all right, 5.86. So you will know phi, okay? So once you know phi, so you can substitute in equation 1, then solve for A, okay? So substitute the value of phi in equation 1 and solve for A. So find out A value from equation 1 because A sine phi is equal to negative 0.04. So therefore, find out the value of A. So let me know once you calculate A value. So let me know your answer for A. So A is nothing but the amplitude. So that is the maximum displacement. That's correct, Azhar. So A, you will get 0.39. So that means the maximum displacement is 0.3911 meters. Okay, so you will get the maximum displacement. So then the equation of motion, you need to substitute. So x value. So now substitute everything in this, you will get the equation of motion. So A, you substitute negative 0.39 sine, then omega n, you will substitute 12.83. T, the phi value, you substitute 5.86 degrees. So that will be your response. So substituting the values of A, omega n, and phi in the general solution, so you will get the equation of motion or the response for the system. Guys, is that clear? So substitute A value and phi value and omega n value in the general solution and write down the general solution. That gives you the final answer. So the maximum displacement is of course A, which is negative 0.3911 meters. So this will be the complete solution for the question. So I think one of your question you may have to do similar analysis. Is that okay, guys? Any questions? Uh, 0.039. Yeah, I think you need to be careful about this. Or 0.39. So you can check your calculations. I think earlier you wrote 0.039. I think 0.39 is correct, sir. Okay, we'll have a time to look one more question. Okay, so you may look at this example. So this is one of the questions in the past class test. Okay, so there's a mass and spring system is given. The mass is there. The damping constant is there. Initial displacement is 0. And the initial velocity is 10 meters per second. Okay, so the first part of the question asks you, what is the damping ratio? So to calculate the damping ratio, so you need to calculate the critical damping constant Cc. So to calculate that critical damping constant, so the formula is 2 square root of Km. Okay, so you can get C, the critical damping constant. So once you know that, then you can calculate the damping ratio, C over Cc. Guys, can you tell me your answer for damping ratio? That's correct, Eva. So you get, is it? No, not 7.5. It is 0.75. That's correct. So eta, you will get 0.75. So if the damping ratio is 0.75, is it over-damped or under-damped? So is the system under-damped or over-damped? So the answer is under-damped. Why? So why? Because eta is less than 1. That's correct. So eta is less than 1. So the next part is calculate the damped natural frequency. So for 3, you can write the damped natural frequency is omega d is equal to omega n into 1 minus eta square. So you can calculate the damped natural frequency. So let me know what is the damped natural frequency. That's correct, 6.67 radians per second. So I just take it as 6.6. So whatever the value you get, you can write. Then the response of the system, the free vibration response of the system. So you can write in any way x is equal to a sine Okay, so you have the damper also, therefore you need to write the response here as exponential power minus eta omega nt. Then sine omega d plus phi. So we take the response in this particular form. So the initial conditions are, we know at time 0, the displacement is 0. And we know at time 0, the velocity is 10. Okay, so these are the two initial conditions. So now the first one, when we apply the initial condition here, so this will be 0. So 0 will be so a into exponential power 0. Okay, and sine 0 is 0, so you will have a sine phi. So sine phi is equal to 0. So that means, so you know that the phi is also 0. Because sine 0 is 0, so that means the phase is 0. All right, so for the next part, so you need to take the derivative of this equation. So to apply the second condition, so to apply the second initial condition, we need to take the velocity. So velocity means you need to differentiate this expression. So once you differentiate this expression, so x dot will be, okay. So I just write minus eta into omega n, okay, amplitude A, then exponential power minus eta omega nt into sine omega dt plus phi. So we have to do the product rule here, differentiation product rule. Okay, so plus a omega d exponential power minus eta omega nt so cosine omega dt. Okay, so this will be the velocity when you differentiate this expression. So you will get the velocity x dot like this. So now we replace time t is equal to 0 and x dot is equal to 10. So replacing this, okay, so you can, so now substitute everything, eta into omega n. So omega n value will be there, eta value is there. So you calculate it, right? So you can calculate what will be the value of this. Okay, so then if you put t is equal to 0, so this will be 0. So then this will be 0 also. Okay, so then from substituting the x dot is equal to 0, but velocity is 10. So calculate a into omega d. So when you put time t is equal to 0, I think your final, you get only a into omega d. So the whole thing becomes 1. Okay. So from this, you can calculate a is equal to 10 over omega d. So because sine 0 is 0, so the whole thing will be 0 here. So that leaves you only a into omega d. So cos 0 is 1 here, so this is 1 here. So that only gives you a omega d is equal to 10. So then you calculate what is a value. So substitute a value in this expression, that will give you the final response. Because you know omega d, therefore you can calculate a value. So a value, I think you will get about 1.51. So substitute a value here. Okay, substitute a value. Okay, so this portion eta into omega and t, you can replace whatever is the number. Okay, so you can substitute whatever is the number here, then substitute the phase. So that will be the final free vibration response of the system. All right, guys. So any questions on this? So this will be something similar to your question 3 and question 4. Okay, so all right, I'll stop here. Then I think Prasad will take over from here. Um, meanwhile, if you guys have any doubts, you can always email. Then we can still communicate through email if you guys have any doubts. Okay, so don't miss Professor Park's pre-examination workshop and carefully take the notes. He'll be able to give you. So he'll be able to give you enough indications about the type of questions. All right. So I'll stop here. We have a few more minutes. Any questions? Let me know. Can explain the last part after substitute A. So you just write down A value 1.51. So exponential eta into omega n. So omega n value, okay, you calculated omega n. You can calculate k by m under root, right? So eta value you already know. So eta into omega m will you get a number. Okay, you get a number. So you just write that number here. Okay. So omega d is also here. So you just replace omega d value. So phi value is anyhow 0. So you just write the final response indicating the A value and this value. Is that okay, Darren? All right, guys. So any other questions, let me know. So generally, my suggestion is you need to spend more time for solid mechanics and okay, relatively less time may be required for vibrations. So solid mechanics, the good thing is that uh, all the equations are straightforward. So only thing is you need to know how to calculate quickly. So because a lot of calculation is involved and the calculation, the numbers always goes into 10 power 6, 10 power 9, big numbers. So calculation will take time. So in the past several years, I know nobody failed for mechanical vibrations, but yes, some students find it difficult solid mechanics, and they may sometimes get below 50 marks. All right, guys, any other questions? Let me know. I stop here. I stop recording. Okay. So if you guys have no other questions, then you can